So now let's look at how we can apply principal components analysis to real-world problems. And we'll use the data sets that we've been using for this lecture. And then after that, we'll summarize what we've learned in this lecture. So Richard Hamming said the purpose of computing is insights, not numbers. But this lecture, we've spent most of our time digging through numbers. And I want to step back so that you can understand why this is useful. And to do that, we're going to do some exploratory data analysis. And we're going to use the tool that we've covered in this lecture of principal components analysis. So, goal here is we want to take high-dimensional data and plot it as two-dimensional approximations that we get from some linear combination of the attributes. The related goal here is to determine whether this two-dimensional plot that we have really shows the variability in our data. If the answer is no, it doesn't capture the variability in our data, then we want to be really careful of any conclusions that we might draw from using principal components analysis to develop that plot. Now, to do that, let's dive into our notebook and look at some real data. Okay, so we're going to use our body measurement and congressional voting data sets. And so if we take a look at the body measurements data set again, there are lots and lots of measurements, some of which I don't know what they actually mean, but let's just explore the data and see what we can learn from it. So the first thing that we're going to need to do is to do a singular value decomposition. All right, so first let me just show you the beginning of the data. Then we're going to do our singular value decomposition, and what we see is that we can now compute so we see our principal components. We can now look at what is the fraction of the variance, the percentage of the variance that gets captured by each of those principal components. And we're just going to use the function that we had in this lecture to look at okay. So something's not quite right here, right? Because what this is telling us is that the first principal component is capturing 99% of the variance in our data set. And we know that there are attributes that are independent. Age and weight, or age and density, are relatively independent attributes in our data set. So that our data set could be completely characterized by a rank 1. It doesn't make sense. So what's going on here? Think, what did I tell you? If the results you get from doing singular value decomposition don't make sense, what did you forget? Or in this case, what did I forget? I forgot to center the data, right? Without centering the data, you're going to get ridiculous results like this that don't make any sense, because the y-intercept is going to be through 0, even if the data does not actually have a y-intercept that goes through 0. Okay, so now we're going to center it, and all we do to center it is take, for each column here in our original data set, we compute the average, and then for each value we subtract the average from the value. And so we're going to end up with, you can see here, this person has 6.3% less Brozic fat than the average person in our data set of 100 individuals, 52 individuals. Okay, so now we can do our singular value decomposition, and now we will look at the principal components that result. And they now seem to be a little bit more realistic, and so we can actually compute our values. And yeah, so we can see here that the top two principal components are capturing, 91% of our variance. We add in the third and we get to 97. So and then the rest are just 1% or less, and we have many zeros. So we can see now that, using the top 2 or 3 is going to capture most of the variance in our data. And of course, we can do the scree plot, and we can see, the same thing, that most of our variance is captured in the first 3 principal components. So, given that these first 3 principal components account for the vast majority of the variance, let's see what happens if we do a rank 3 approximation. So we've got our function that will let us compute that. And one of the things I'm going to do is I'm going to uncenter the data by adding back in the mean of the original data set for each column. Okay, so here is our rank 3 approximation data. And just for easy reference, let's look at our original data again. Okay, so when we look at it, we can see that it's a pretty good approximation. It's not great, for example, 13.7 here, 12.6, so it's a little off, 12.3 here, 13.4 here. Densities are pretty close, 1.07, 1.06. Ages are pretty close, 23.4 and 23. Weights, 154.25, 155. So some of these are, a little bit closer, a little bit further. But we've captured, 6.9, 6.9, 24.6, 24.3, 10.9, 10.4, 27.8, 27.3. We're doing a fairly good job with just those 3 principal components. So who would have thought that, we could capture all of these different measurements with just 3 principal components? Now, one of the things we could do is look at the principal components themselves and plot them relative to each other. So we'll just plot, to make it easy, we'll just plot a 2-dimensional plot of the first principal component versus the second principal component. Okay, and so what we end up with is this. So this is kind of interesting, right? One, our data, does seem to be relatively clustered, but it's hard to really tell what structure there is or what the principal components are representing from just looking at this data. But what do we see that, might make us want to take a deeper look at some of the data? So take a look at this graph. What do we see that might raise some, wonder what that means? Well, what about this point all the way over here on principal component 1, right? That's kind of an outlier. So before we saw that sometimes there was dirty data. Is this an instance of dirty data, or is there something interesting going on? So we can just identify who that largest person on our principal component 1 is, and it's observation 38. And so we can actually look at individual 38's data. And what do we see? Well, when we look at this, the thing that really kind of pops out is their weight is very large, 363. And similarly, the fat-free weight also is very large. And many of the measurements also are large. So this is an interesting individual, and maybe we should look further into this individual. They're also kind of skewing our data set a little bit. So one thing we might want to do is remove this individual from our data set and see, can we see new structure in our first 2 principal components by doing that. I'm not going to do that today, but you can do that and see what you can discover. Okay, so the other data set that we have to work with is our election data set. And so our election data set represents members of Congress, and then it also contains their votes from the month of September in 2019. So here we can see this is their names, their ID, gender, state that they represent, chamber, and then their party and birthday. Then we also have roll call data, roll call vote data for those individuals. And again, the relationship here is that the legislative ID in this table is the same as the member attribute in this table. And then for each of the votes, so each of the roll calls, we have whether they did not vote, or they voted yes, or they voted no. So there are three choices: did not vote, voted yes, and voted no. But we're going to collapse that down to just a binary choice between yes, they voted, will be a 1, or 0 if they did not vote or they voted no. And that's what this function will do for us. Okay, so we have 441 members who voted across 41 different votes. Okay, and so now we want to see, what are some of the trends? What can we extract from this 41 attribute, rank 41, what appears to be rank 41 data. Okay, so we know we need to center, so we're not going to try and do anything before we center our data. So now we've centered our data, and so we can do our singular value decomposition, and we can look at our principal components. And what we discover is that much fewer than 41, our rank is much less than 41. We have a lot of zeros here in our principal components, but our first principal component captures 80% of our variance, and then 5%, and then 2%, and then a lot of 1% principal components. So again, we can do our scree plot, and here again you can see 80% in the first, and then 5%, 2%, and so on. Okay, so now we could do now the question we could ask is, what is that 80% capturing? If we go back to our votes, what is that 80% telling us about the votes and the members? And if I had to make a guess, knowing what I know about the data, my first intuition would be maybe that 80% is related to party, that people vote along party lines by and large. And so we can explore that and determine whether that's actually true. All right, so we can plot a plot of our first principal component on the x-axis and our second principal component on the y-axis. And what do we see? Well, looking at the data, we see two clusters, right? There's a cluster to the left of less than 0 for our first principal component, and there's a cluster to the right for our first principal component, so greater than 0. And then when we look at our second principal component, we see that most of the people, I'd say most of the people fall above -1, and then we have some number that are below -1 for our second principal component. All right, so let's just ask a question. So if we look at principal component 1 and we look at all the people on the left of that principal component 1 being 0, so we draw a vertical line at 0 and we look at all of the people to the left of that line, we find that there are 228 Democrats and there is 1 Republican when we look at the party. So that's interesting. All right, well, what happens if we look at above principal component 2 being -2, and we look to the right, so of principal component 1, so greater than 0. So we're really looking at this group up here. Well, what you discover is that we have 190 Republicans. So that's interesting. So almost all of the people except for 1 to the left of principal component 1 being 0 are Democrats. And then if we look at this upper right corner above -2 and to the right of 0, we find that they are all Republicans. So that's kind of interesting. So we've discovered something from looking at this voting data that's kind of interesting. Now, to make this a little bit easier, we can set the party to be the hue. And now what do we see? Okay, So as expected, we see Democrats over here, and it's just an artifact of the SVD that it happens that the Democrats are on the left and the Republicans are on the right. It could easily have been the reverse. Okay, so, and then we see that the Republicans here are clustered up here in the right, and then interestingly, our libertarian, our independent, is in the middle. That's not surprising. And then we have some Democrats down here and some Republicans down here also. Now, there may be some overplotting, so we could do some jittering. And this does help a little bit. We can see, the numbers, of individuals. Now it becomes a little bit more apparent how many people we have in each location by doing that jittering. We can see actually there are quite a number of Democrats down here with our principal component, our second principal component, less than -2. Okay, so now we can take and add those principal components. So for each member of the house, we could add in their principal component. So their first principal component and their second principal component. All right, and so now, again, if we look at principal component 1 greater than 0, so just looking to the right of this vertical line at 0, we find that there are 195 Republicans that voted on that, 7 Democrats and 1 Libertarian. Okay, so that's interesting. Again, we're exploring the data. We can see that principal component 1 does seem to be capturing something about party affiliation, but it's not complete. Now let's look at the people below principal component 2 being -1. And so we want to see what's going on with principal component 2. What is it capturing? Can we figure that out by looking at the data that we have on hand? All right. So the first thing we'll do is we'll actually just look at the data and see what we can find. Okay. So we see our libertarian, Justin Amash, Ralph Abraham, who's a Republican, Dan Bishop, who's a Republican, James Clyburn, who's a Democrat, and so on. And so nothing immediately pops out by looking at this. Again, we could go and Google each of these congressmen and see, what their sort of plank is for their voting strategy, and see if we could see something that matches what we're seeing in where they fall in the second principal component. But we can also use the data that we have, and we could look at how they have voted. And so if we look at member 367, we can see that they voted no 31 times and 10 times they voted yes. If we look at Ralph Abraham, we can see that, well, interestingly enough, he didn't vote. He didn't vote 41 times. He missed all of those votes. If we look at B1311, we can see they voted no 17 times, they voted yes 7 times. Here's another person who didn't vote 37 times. Another person who didn't vote 23 times. Another person who only voted yes 6 times and didn't vote 1 time. And so on. And so what we might, and then, here's an interesting thing. It turns out there's another category of vote. There is voting as the speaker, right? So, 197, Nancy Pelosi, she voted as the speaker. And so her votes got counted, differently and reported differently in this data set. And so what we start to see is, maybe what's being captured here is that the lower value of principal component 2 means they didn't vote as much. That might be one of the things that it's capturing. So let's look at people who have only look at the people who have voted more than 15 times. Okay, and so if we look at that, Now what we're going to do, just got to have some helper functions to help me. So we're going to now look at just the regulars. And what we can see here, so we went from 441 members to 425. Still have 41 votes, but we've now reduced the number of people that we're going to look at to the people who vote on a regular basis, as opposed to the people who are not voting. Okay, so now we can plot our scatter plot. And so now you can see we've changed the y-axis, right? Because we've effectively dropped many of those people who didn't vote, that had the lower principal component 2 values. All right, and so we can do some jittering so that we can make it a little easier to see this, and we can also add in the party. And so now we can see, unfortunately, this is covered up a bit. There are a few, there is the one Republican who shows up on the left side here, less than 0 for PC1, but almost all of the Republicans show up on the right side of greater than 0 for PC1. And then here's our independent. He's in the middle and has a lower PC2 score. So this is just one of the types of explorations that we can do of data like this. And what you can see is we've been able to take our high dimensional data, 41 different votes, and really reduce it down to a very small number of principal components that capture useful information. So just with looking at our first and second principal component, we've been able to separate out and identify the party of the individuals. Okay. So returning back to our slides. So when you're doing principal components analysis, it's going to be appropriate to use that for exploratory data analysis if the following holds true. If you're trying to visually identify clusters of similar observations in high dimensions, right? If I had tried to plot that 41 dimensional data of all those votes, we would not have been able to extract any useful information. In fact, trying to plot 41 dimensions, I don't even know how we would visualize that, right? And so using principal components analysis, we were able to reduce that data down to a 2-dimensional approximation where those results were really quite apparent. We could easily separate, in this case, party affiliation from that data. Now, it's also important that you use EDA, PCA for EDA, when you're still exploring the data, right? If I already know what I want to predict, then I don't need to use something like principal components analysis. So it really makes sense if I'm still just in this curiosity phase, I've got an open mind, and I just want to explore the data and see where the data takes me. Now, the other important thing is you have to have some reason to believe that the data has an inherently low rank. Because if there are lots of attributes and there is no way to reduce that to lower rank, then PCA isn't going to be able to extract anything useful, right? But here we had many attributes, but there were only a few that actually made a difference, right? And we were able to extract these unobserved attributes. So party was something that we were able to extract from the data set, right? And that was basically determined by this linear association that was applied to all of the 41 dimensions of the vote. Okay, so singular value decomposition is a way of describing a matrix decomposition. It decomposes our input matrix X into U, sigma, and V transpose, right? And U and V have the properties that they're orthonormal, and sigma has the property that it's a diagonal matrix. Now, if our input matrix X has rank R, then it means that there are going to be r non-zero values on the diagonal of our matrix sigma. The values in sigma, we call those singular values, and they're ordered from greatest to least value. The columns of U are our left singular vectors, and the columns of V are our right singular vectors. And principal components analysis is just a very specific application of singular value decomposition. The important thing that we do is we take X and we center that at the mean of each column. And that's the critical step. Do not forget that step, otherwise your principal components analysis will yield useless results. It'll be garbage in, garbage out. So make sure you center your data matrix first, and then you apply singular value decomposition. The largest n singular values, we keep those for some choice of n, right? And then we set all the other singular values to 0. This is the dimensionality reduction step that we do. So we pick the choice for what n is going to be. That's going to control what the rank of our approximation is going to be. If we make it equivalent to our input rank, then we'll end up, our input dimensionality rather, then we'll end up with the most accurate representation. And then as we reduce it, again, throwing away columns that are 0 or throwing away columns that are relatively small, we're going to have more and more of an approximation as an end result. Okay, so the first n rows of V transpose are the directions for our n principal components. And the first n columns of our U sigma matrix, or XV, are going to contain the n principal components of our input data set X. Okay, now primarily we're going to utilize U sigma by plotting the first two columns and a scree plot of sigma. So instead of looking at U sigma, we could instead look at V transpose, right? A principal component direction is just going to be a linear combination of a set of attributes, right? And they're given as rows of our V transform matrix, and plotting the values of those first principal component direction can give us some insight into how the attributes are being combined. So we can look at that and see, what's the directionality, what is the relationship between that and our input data. So the high variance attributes, typically those are the ones that we want to include because they'll capture the highest variance in our input data set. But it's not always going to be the case that you want to capture those attributes. And then we'll include some of the other attributes, even if there's just a few that are the really important ones. And interpreting the other principal components oftentimes can be challenging, right? So that first principal component oftentimes gives us that highest variance and variability, and it becomes something that, oh, okay, I understand what it's pulling out of the data set. But oftentimes when we look at the additional principal components, while they add to the accuracy of the rank approximation, it might be harder to understand what they're capturing about the attributes. What are the underlying combinations of attributes that they're capturing? Because they have this constraint that they're orthonormal to the prior components. And so that's going to strongly influence their directions. Okay, so in summary, principal components analysis is a technique that we can use to summarize the data, to reduce the dimensionality of the data. And there's one goal for PCA that we can state two different ways. We want to find directions that minimize the projection error, or we want to find directions that maximize the captured variance of our input data set. So to perform principal components analysis, we use singular value decomposition. There are other alternatives, but that's beyond the scope of this class. The important thing is make sure you center your matrix before you perform the SVD step. Now, if the principal components analysis is successful, then that 2D plot that we get still preserves the structure of the original data. And the scree plots are a way that we can tell how much information is lost, because we can see if we throw away principal components, what is the reduction in capturing that variance that we're going to see.